So I'm going to focus on one-dimensional Gaussian, but you can extend the results that we are going to see here to multi-dimensional Gaussians. The essence of MLE remains the same. As you might see after this example, that the way you apply MLE more or less remains the same, just that the distributions that we are drawing our samples from are different each time. So earlier we saw a Bernoulli trial, which is a discrete probability distribution, and now we are going to look at a continuous probability distribution, which is probability of x. We are going to have two parameters here, a mean and a variance sigma square. Remember that the mean that we are going to denote here is different from what we saw earlier on for the other distribution. And the mathematical expression that relates x with mu is so this is the parametric form of Gaussian distribution. Very crudely, a Gaussian distribution looks like this, where this is the mean and your sigma square would be approximately distributed like this. And your Gaussian distribution, as you can see, extends over the entire real axis. And for every single point on the x-axis, you can find the probability density. This is point xi. You can find out the probability density. Now again, let us assume that we have a sample set D of samples that you have already obtained from the Gaussian distribution, and let us denote it by x1 until xn. So we have n samples that we have already sampled from the Gaussian distribution, and our goal is to estimate the parameters mu and sigma squared. So like how we estimated the parameter mu in a Bernoulli distribution earlier on, now we are going to get a maximum likelihood estimation of mu and sigma square. So the first step in maximum likelihood estimation would be to write the likelihood function. So the likelihood function here is going to be, again, is going to be probability of getting D given mu and sigma squared. And this is going to be probability that we have obtained x1 until xn given mu and sigma squared. And we are going to assume that x1 until xn belong to IID. So what this would mean is that this would become a product of probability of xi given mu sigma squared. Like before, we are going to take the log of the likelihood function, and we are going to convert the product into a summation. And we are going to equate the log of this function to 0, right? We want to, sorry, not the log of this function, but the derivative of the log of this function to 0. So once we have the log likelihood, we're going to do the derivative of log likelihood over the parameters, and we are going to set it to 0. So if you want to recall, probability of xi given mu sigma squared is given as 1 by root 2 pi sigma multiplied by an exponential function like this, x minus mu the whole squared over sigma squared. It is going to be xi minus mu the whole squared minus n over 2 log sigma squared minus n over 2 log of 2 pi. So you can see that if you take the logarithm of this function, you would end up with this for the summation. So now that we have this, as you know, we are going to take the derivative of the log likelihood and set it to 0. So first I'm going to differentiate with respect to mu and then find out mu ml. So when I differentiate this expression with respect to mu, I know that these two are going to go to 0 because they are not dependent on mu. So I'm going to get 2 times I equals 1 to n xi minus mu equals 0. So this simplifies to n mu equals sigma I equals 1 to n xi, or my mu ml is nothing but the average of all the xi's that I've obtained so far. Again, this seems intuitively very correct. So if I want to find out the mean of a distribution from which I have sampled a lot of samples, then I just take all the samples that I have and calculate the mean of those samples. What about the variance? So to just recall, we had the log likelihood function as so I'm now going to differentiate this with respect to sigma squared. I'll know that this term will go to 0 because it will not depend on sigma squared. And now, instead of having mu here, since I already know what mu ml is, I'm going to take this as mu ml. So this is going to be negative 1 over 2, and I have a sigma squared here, so I'm going to get sigma squared to the minus 2 into sigma I equals 1 to n xi minus mu ml the whole squared. And since I differentiated with respect to sigma squared, this negative sign is going to become a positive sign. And this term would become 1 over sigma squared. And I'm going to equate it to 0. So I'm going to cancel 1 sigma squared, and I'm going to get 1 over 2 sigma squared times this expression equals n over 2. Again, I'm going to cancel the 2 and take the sigma squared here. So I'm going to get sigma squared ml equals 1 over n, sigma I equals 1 to n xi minus mu ml the whole squared. So this is the maximum likelihood estimate of my variance from the data that I have already obtained. So as you can see, you can apply this technique to many distributions. So you need not even have the assumption of IID, just that it simplifies the mathematical expressions that we obtain.